Try something for me right now. Take any object near you. A pen, a cup, your phone. Hold it in your hand. Now tell me exactly where it is, and exactly how fast it's moving. Seems simple, right? You can see it, you can measure it, you can describe its position down to the millimeter, and its velocity down to the centimeter per second. You have certainty, complete, absolute certainty about this object's state in reality. But here's the truth that's going to shatter everything you believe about knowledge, about measurement, about the very nature of what it means to know something. You're wrong. Completely, fundamentally, absolutely wrong. And Werner Heisenberg proved it in 1927 with a discovery so disturbing, so completely alien to human intuition that even Albert Einstein refused to accept it for the rest of his life. Heisenberg discovered that certainty is a lie, not a philosophical opinion, not a matter of better instruments or more careful measurements. A fundamental law of the universe itself. Nature forbids certainty. The cosmos has built into its very fabric an absolute, unbreakable limit on what you can know. And this isn't about your limitations as an observer. This isn't about technology. This is about reality itself, refusing to be pinned down, refusing to be known completely, refusing to exist in the way you think it exists. Let me ask you again, but this time think carefully. Where is that object in your hand, and how fast is it moving? You think you know, you feel certain, but Werner Heisenberg is about to prove to you that your certainty is an illusion, that knowledge itself has limits, that the universe fundamentally, irreducibly, permanently refuses to let you know everything about anything ever. This is the uncertainty principle. And once you truly understand it, once it really sinks into your bones, you will never see reality the same way again. Because Heisenberg didn't just discover a limitation of measurement. He discovered that reality itself is uncertain, that particles don't have definite positions and definite velocities at the same time, that the universe is fundamentally probabilistic, that certainty is not just difficult to achieve, it's impossible. It's forbidden by the laws of nature. You learned in school that science is about precise measurements, exact predictions, certainty. Newton's laws could predict the position of planets centuries in advance with perfect accuracy. Classical physics was a machine of certainty. You input the initial conditions, you run the equations, you get the exact future state. Deterministic, predictable, knowable. The universe was a clockwork mechanism, every gear perfectly defined, every motion completely determined. But Werner Heisenberg destroyed that worldview completely. He proved that, at the most fundamental level, the level of atoms and electrons and photons, certainty doesn't exist, can't exist. The universe itself forbids it. And here's what makes this so profoundly disturbing. It's not about our ignorance. It's not that the electron has a definite position and momentum, but we just can't measure both. It's that the electron doesn't have both. Reality itself is indefinite. The particle exists in a state of fundamental uncertainty until you measure it. Think about what this means. Really think about it. The objects you see around you, the solid matter you touch, the predictable world you navigate every day, all of it is made of particles that don't have definite properties. Particles that exist in clouds of probability. Particles that literally don't know where they are or how fast they're going until something forces them to decide. Your entire reality is built on a foundation of uncertainty, of indefiniteness, of fundamental unknowability. Now, you might be thinking, wait, this sounds like philosophy, like abstract speculation, but it's not. This is physics, hard, mathematical, experimental physics. Heisenberg didn't philosophize about uncertainty. He proved it with equations. He derived mathematical relationships that put absolute limits on measurement precision. And then experimenters verified it thousands of times. The uncertainty principle isn't theory, it's fact. It's as well established as gravity, as well proven as the roundness of the Earth. Let me show you exactly what Heisenberg discovered. Take a particle, an electron. You want to know where it is. You want to know its position in space. To measure position, you need to interact with the electron somehow. The most straightforward way is to bounce light off it. A photon hits the electron, scatters. And from the scattered light, you can determine where the electron was when the collision happened. Simple, direct. This is how we see everything in the macroscopic world. But here's where reality gets strange. To measure position very precisely, to pin down exactly where the electron is, you need light with a very short wavelength. Short wavelength means high energy. It's the only way to get the resolution you need. Long wavelength light is fuzzy, imprecise. It can't give you exact position. You need sharp, short wavelength photons to measure position accurately. But here's the problem that Heisenberg realized, the insight that changed physics forever. When that high-energy photon hits the electron, it doesn't just bounce off gently. It kicks the electron hard. The photon transfers momentum to the electron, changes its velocity, disturbs its motion. And the more precisely you want to measure position, the shorter the wavelength you need. The higher the energy, the harder the kick. The more you disturb the momentum. So measuring position precisely destroys your knowledge of momentum. The act of pinning down where the particle is scrambles information about how fast it's moving. You can't avoid this. It's not a matter of being more careful or using gentler instruments. It's fundamental. The very act of measuring position with precision necessarily disturbs momentum. The better you know position, the worse you know momentum. And it works the other way too. If you want to measure momentum precisely, you need long wavelength light, gentle photons that don't disturb the particle much. But long wavelength light gives you terrible position information. It's too fuzzy to spread out. It can tell you the electron's momentum accurately, but it can't tell you where the electron is. The better you know momentum, the worse you know position. Heisenberg captured this in a mathematical inequality, an equation so simple and so profound that it defines the limits of knowledge itself. The uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to Planck's constant divided by 4 pi, always, without exception, forever. This isn't a law about measurement technology. This is a law about reality itself. Let me translate that into plain language. You cannot know both the position and the momentum of a particle with perfect precision. Not because you're not smart enough. Not because your instruments aren't good enough. But because nature itself forbids it. The universe has a fundamental limit on knowability built into its structure. Certainty is impossible. Reality refuses to be completely known. Now you might think, okay, but surely this is just about tiny particles. About electrons and photons. Things I can't see anyway. My everyday world, the world of coffee cups and cars and buildings. That's still certain, still predictable, still knowable, right? Yes and no. The uncertainty is there. It's always there. It's fundamental to every particle that makes up every atom in your body, in this room, in the entire universe. But the effects are so small at macroscopic scales that you don't notice them. For an electron, the uncertainty is significant, measurable, impossible to ignore. For a baseball, the uncertainty is so tiny, so unimaginably small, that it's completely negligible. You can know the position and momentum of a baseball to any practical precision you want. The uncertainty is still there, but it's buried beneath the level of measurement sensitivity. It's real but irrelevant for everyday purposes. But here's what's crucial to understand. The everyday world isn't exempt from uncertainty. It's just that the effects are hidden by scale. The baseball is made of trillions upon trillions of atoms, and the individual uncertainties of all those atoms average out to something so small you can ignore it. But remove the atoms one by one, shrink the object down to the quantum scale, and the uncertainty becomes dominant, becomes the most important feature of reality, becomes the thing that defines what the object even is. And this leads to something even more disturbing, something Heisenberg realized, but that took decades for physicists to fully accept. The uncertainty isn't just about measurement, it's about existence itself. Before you measure an electron's position, it doesn't have a definite position. It's not that it has a position you don't know, it's that it doesn't have a position at all. It exists in a state of superposition, spread out over space, described only by probabilities. The electron is a cloud of possibility until you measure it. And when you measure it, when you force it to interact with a measuring device, the cloud collapses. The electron suddenly has to pick a definite position. The act of measurement creates definiteness, where before there was only probability. Reality crystallizes from possibility into actuality. At the moment of observation, this is what drove Einstein crazy. He famously said, "God does not play dice with the universe." He believed there had to be hidden variables, underlying deterministic properties that we just couldn't access. The uncertainty, he thought, was about our ignorance, not about reality itself. But Heisenberg said, no. The uncertainty is real. The dice are fundamental. The universe is probabilistic at its core, and there's no deeper level of hidden certainty underneath. And Einstein was wrong. Decades of experiments have confirmed it. Bell's theorem in the 1960s proved mathematically that local hidden variables can't exist. The quantum experiments of the 21st century have verified the uncertainty principle to extraordinary precision. There are no hidden properties determining everything in advance. The uncertainty is real. The probabilities are fundamental. Reality really is indefinite until you measure it. Now, let me show you something that makes this even more mind-bending. The uncertainty principle doesn't just apply to position and momentum. It applies to energy and time. The more precisely you try to measure the energy of a system, the less precisely you can know when that energy was measured. Energy and time have the same fundamental trade-off as position and momentum. They're complementary variables, linked by the uncertainty principle. And this leads to one of the strangest consequences of quantum mechanics. Something called virtual particles. Because energy and time are uncertain. Because you can't know both precisely, the universe allows temporary violations of energy conservation. For incredibly brief moments, particles can borrow energy from nothing. Pop into existence spontaneously, exist for a fleeting instant, and then disappear, paying back the energy debt before anyone notices. This isn't speculation. This is measured reality. The vacuum of space, what you think of as empty nothingness, is actually seething with virtual particles constantly appearing and disappearing. Electron-positron pairs, blinking in and out of existence. Quarks and antiquarks, emerging from nothing and annihilating back to nothing. The vacuum is not empty. It's a bubbling foam of quantum uncertainty, of particles borrowing energy for microseconds, existing on credit from the universe's energy-time uncertainty. And you can measure this. There's an experiment called the Casimir effect, where two metal plates, placed very close together in a vacuum, are pushed together by the pressure of virtual particles. The virtual particles outside the plates outnumber the virtual particles between plates because some wavelengths can't fit in the narrow gap. This creates a measurable force. Empty space pushes matter. The uncertainty principle has real, physical, measurable consequences. Think about what this means. The foundation of your reality, the vacuum between atoms, the empty space between particles, is not empty. It's uncertain. It's fluctuating. It's filled with ghostly particles that exist only because the universe's accounting system for energy and time is fuzzy enough to allow temporary loans. Reality itself is probabilistic, uncertain, fundamentally indefinite. And this isn't a bug. This is a feature. This is how the universe works. Now let's go back to Werner Heisenberg himself because his story makes the discovery even more remarkable. In 1925, Heisenberg was only 23 years old. 23. Barely out of university, and he was suffering from terrible hay fever, miserable, unable to focus, desperate for relief. So he left his work in Göttingen and traveled to Helgoland, a barren island in the North Sea, with clean air and no pollen. And there, alone, isolated, free from distractions, he had one of the greatest insights in the history of physics. He was struggling with a problem that had tormented physicists for years. The old quantum theory of Niels Bohr could predict some properties of atoms, but it was incomplete, inconsistent, full of ad hoc rules that worked but made no sense. Physicists knew something was fundamentally wrong with their understanding of atomic structure. They needed a new framework, a new way of thinking about quantum phenomena. But every approach seemed to lead to contradictions. Heisenberg decided to do something radical. He decided to abandon visualization entirely. Classical physics had always relied on mental images, on picturing what was happening, on constructing models you could see in your mind's eye. Electrons orbiting the nucleus like planets around the sun, waves rippling through space, particles bouncing like billiard balls. But at the quantum level, these visualizations kept failing, kept leading to paradoxes. So Heisenberg threw them out. He said, let's only work with things we can actually observe. We can't see electron orbits. We can only see the light electrons emit when they jump between energy levels. So let's build a theory based only on observables, on measurement results, on what we can actually detect. Forget about what's happening between measurements. Focus only on what we can measure before and after. This was revolutionary. It was a complete break from how physics had been done for centuries. And it worked. Heisenberg developed matrix mechanics, a mathematical framework that described quantum systems without reference to underlying pictures or mechanisms. It was abstract, it was algebraic, it was purely about relationships between observables, and it made predictions that matched experiments perfectly. But here's what really matters. In developing this framework, Heisenberg discovered something deeply disturbing. The mathematics itself contained the uncertainty principle. It wasn't something he added in. It fell out naturally from the structure of the theory. The position operator and the momentum operator in quantum mechanics don't commute. They don't play nicely together. Measure position, then momentum, and you get a different result than if you measure momentum, then position. This non-commutativity, this mathematical fact that the order of operations matters, directly implies the uncertainty principle. It's built into the math. It's unavoidable. If you accept quantum mechanics, if you accept that Heisenberg's equations correctly describe atomic behavior, then you must accept that position and momentum can't both be known precisely. The uncertainty isn't an add-on. It's fundamental to the structure of quantum theory itself. And Heisenberg realized this in 1927. 2 years after developing matrix mechanics, he was back in Copenhagen, working with Niels Bohr, and he was thinking about measurement, about what it means to observe a quantum system. And he derived the famous uncertainty inequality, the mathematical relationship that puts limits on how precisely you can know complementary variables. He published it in a paper that changed physics forever. But here's the truly fascinating part. Bohr didn't agree with Heisenberg's interpretation. Not at first. Bohr thought Heisenberg was focusing too much on the disturbance caused by measurement. Bohr believed the uncertainty was more fundamental, more about the wave-particle duality, about the fact that quantum objects exhibit both wave and particle properties depending on how you measure them. The two men argued intensely. Heisenberg even cried during their debates. The disagreement was that passionate, that profound. Eventually, they reached a kind of synthesis, what became known as the Copenhagen interpretation of quantum mechanics. But the core insight remained Heisenberg's. Certainty is impossible. The universe doesn't permit it. Reality is fundamentally uncertain, and there's no way around it. No deeper level of hidden determinism. No escape from the probabilistic nature of existence. Now let's think about what this really means for your daily life, for your understanding of reality. You've been living your whole life under the assumption that things have definite properties, even when you're not looking at them. Your car is in your garage with a specific position and velocity, even when you're not measuring them. The moon is in a definite place, even when no one is observing it. Objects have objective properties, independent of observation. But the uncertainty principle says this is wrong. At the quantum level, particles don't have definite positions and momenta until you measure them. They exist in superposition, in a cloud of probability. The electron doesn't have a position, it has a probability distribution for position. And when you measure it, the probability cloud collapses to a single definite outcome. Measurement creates reality, rather than revealing pre-existing reality. And yes, this is about tiny particles, about electrons and photons. But you're made of electrons and photons. Every atom in your body, every molecule, every cell, is composed of quantum particles that individually don't have definite properties. The definiteness of your macroscopic body emerges from averaging over countless uncertain quantum particles. Your apparent solidity, your apparent certainty, is a statistical illusion created by vast numbers. Peel away the layers, zoom into smaller and smaller scales, and the uncertainty becomes dominant. Remove enough particles, and the quantum uncertainty starts to affect macroscopic behavior. This is how quantum computers work. They exploit the uncertainty, the superposition, the probabilistic nature of quantum particles to perform calculations that classical certain computers can't do. The uncertainty isn't a limitation to overcome. It's a resource to exploit. And here's something that will really twist your mind. Some interpretations of quantum mechanics suggest that observation itself, conscious observation, plays a role in collapsing the wave function, in turning probability into actuality. The universe is uncertain until someone looks, and then it decides. This doesn't mean consciousness creates reality in some mystical sense. But it does suggest that the boundary between observer and observed is much fuzzier than classical physics assumed. You are not separate from the system you're measuring. You're part of it. Your interaction with the quantum system changes it fundamentally. There's no way to observe without participating. The observer and the observed are entangled, linked, interdependent. You can't step outside the universe and look at it objectively. You're always inside, always interacting, always participating in the creation of definite reality from indefinite possibility. This is what Heisenberg understood more clearly than almost anyone. The uncertainty isn't a practical limitation. It's telling us something profound about the nature of reality itself. Reality is not a collection of objects with definite properties existing independently of observation. Reality is a web of interconnected processes, of measurements and observations, of probabilities collapsing into actualities. The universe is participatory. You're not just observing reality, you're helping to create it with every measurement you make. Now let's talk about what happens when you try to cheat the uncertainty principle. Because people have tried. Physicists have spent decades designing clever experiments to try to measure both position and momentum more precisely than Heisenberg's limit allows. They've used sophisticated techniques, quantum tricks, ingenious setups. And every single time, the uncertainty principle wins. Nature always finds a way to enforce the limit. One famous attempt involves something called squeezed light. The idea is to reduce the uncertainty in one property, say position, by allowing the uncertainty in the complementary property, momentum, to increase. You squeeze the uncertainty in one direction, and it bulges out in the other. Like squeezing a balloon, you can reshape the uncertainty, redistribute it, but you can't reduce the total amount. The product of the uncertainties always stays above Heisenberg's limit. Another approach involves entanglement, using pairs of particles that are quantum mechanically connected. Maybe you can measure position on one particle and momentum on the other, and somehow combine the results to beat the uncertainty principle. But no, the entanglement doesn't help. The uncertainty is still there, just distributed across the pair. You can't use quantum tricks to get around a fundamental quantum limit. And this makes sense when you really think about it. The uncertainty principle isn't a technological limitation. It's not about our instruments being too crude, or our techniques being insufficiently clever. It's a statement about the structure of reality itself. It's telling us that position and momentum are fundamentally linked, that they're not independent properties, that knowing one precisely necessarily means not knowing the other precisely. They're like two sides of a coin. You can look at one side or the other, but you can't see both sides simultaneously from a single vantage point. Except in quantum mechanics, it's even more fundamental. The properties don't even exist simultaneously. The particle doesn't have both a definite position and a definite momentum. It has one or the other, or neither, depending on what you measure. And this connects to something even deeper, something that Heisenberg hinted at, but that later physicists explored more fully. The wave-particle duality. The fact that quantum objects behave sometimes like particles, localized in space, and sometimes like waves, spread out over space. When you measure position precisely, you're forcing the object to behave like a particle. When you measure momentum precisely, you're forcing it to behave like a wave. The object doesn't have an inherent nature as particle or wave. It has the potential to exhibit either behavior depending on what you measure. The measurement context determines what you see. The universe is contextual. Properties depend on how you look. There's no context-independent, objective reality with definite properties. Reality is relational, participatory, uncertain. Now let me tell you about something that takes this uncertainty to an even more bizarre level. In 1935, Einstein, working with Boris Podolsky and Nathan Rosen, proposed a thought experiment designed to show that quantum mechanics must be incomplete. They imagined a pair of particles created together and then separated by a large distance. According to quantum mechanics, measuring the position of one particle instantaneously determines the position of the other particle, no matter how far apart they are. Einstein argued this was absurd. Either information travels faster than light, violating relativity, or the particles had definite positions all along, and quantum mechanics just didn't describe them. He thought this proved quantum mechanics was incomplete, that there must be hidden variables determining everything in advance. The uncertainty, he believed, was about our ignorance of these hidden variables, not about reality itself. But Einstein was wrong. In the 1960s, physicist John Bell developed a mathematical proof showing that no local hidden variable theory could reproduce all the predictions of quantum mechanics. And then experimenters tested it. They created entangled particles, separated them, measured them, and found that quantum mechanics was right. The correlations between distant particles were exactly as quantum mechanics predicted and incompatible with any hidden variable theory. The universe really is non-local in some sense. Measuring one particle really does instantaneously affect the other particle's state, no matter how far apart they are. But no information travels faster than light. The effect is real, but can't be used to send messages. It's a correlation without a cause, a connection without a signal, and the uncertainty is fundamental. The particles genuinely don't have definite values until you measure them. This is called quantum entanglement, and it's been verified thousands of times. It's the basis for emerging quantum technologies like quantum cryptography and quantum computing. The uncertainty, the indefiniteness, the probabilistic nature of quantum mechanics isn't a bug to be fixed. It's the feature that makes these technologies possible. The uncertainty is real, and it's useful. And this brings us to perhaps the most profound implication of Heisenberg's uncertainty principle. The future is not determined. In classical physics, if you knew the exact position and momentum of every particle in the universe at one instant, you could, in principle, calculate the exact state of the universe at any future time. Everything would be determined, predictable, inevitable. The universe would be a clockwork mechanism, wound up at the Big Bang and ticking forward in a completely determined way. But the uncertainty principle destroys this determinism. You can't know the exact position and momentum of every particle. You can't even know the exact position and momentum of a single particle. The initial conditions can't be specified precisely, and that means the future is not determined. It's probabilistic. The universe is open, unpredictable, genuinely creative. The future is not contained in the past. It emerges, it unfolds. It becomes in ways that couldn't be predicted even in principle. This has profound implications for free will, for consciousness, for the nature of time itself. If the universe is deterministic, if everything is mechanically determined by prior causes, then free will is an illusion. Your choices were determined at the Big Bang. You're just a machine playing out a program written billions of years ago. But if the universe is fundamentally uncertain, fundamentally probabilistic, then there's room for genuine novelty, for choices that aren't completely determined by the past. Now, I'm not saying the uncertainty principle solves the free will problem. It doesn't. Random quantum events aren't the same as meaningful choices. But it does show that the universe isn't a deterministic machine. There's genuine openness, genuine uncertainty at the foundation of reality. And that changes everything about how we think about causation, about time, about our place in the universe. Heisenberg himself struggled with these philosophical implications his entire life. He was trained as a physicist. He thought like a physicist. He wanted to stick to observable facts and mathematical predictions. But he couldn't escape the philosophical questions. What does it mean to say a particle doesn't have a position until you measure it? What is measurement? What role does consciousness play? What is reality? He never found completely satisfying answers. Nobody has. These questions remain open, hotly debated, deeply mysterious. But what Heisenberg did accomplish, what his uncertainty principle definitively established, is that certainty is impossible. The universe refuses to be known completely. Reality is fundamentally uncertain, irreducibly probabilistic, permanently indefinite in ways that no amount of technological progress can overcome. And this is where we need to step back and appreciate just how revolutionary this is. For thousands of years, humans assumed that reality was knowable in principle. We might not know everything now, but with better instruments, better theories, better observations, we could eventually know everything. The universe had definite properties, and our job was to discover them. Knowledge was just about removing ignorance. But Heisenberg proved this is wrong. Knowledge has limits, not practical limits, fundamental limits. There are things about reality that can't be known, even in principle. The universe has an inherent fuzziness, an irreducible uncertainty that's not about our limitations, but about the nature of reality itself. This isn't pessimistic. This isn't sad. This is how reality actually is. And it's far more interesting, far more subtle, far more beautiful than the deterministic clockwork universe we once imagined. Because an uncertain universe is a creative universe. A universe where the future is not contained in the past. A universe where novelty emerges, where possibilities collapse into actualities. Where observation participates in creating reality rather than just passively recording it. You're not a passive observer of a predetermined show. You're a participant in an ongoing process of reality, becoming definite from indefinite possibility. And this connects to something Heisenberg realized late in his life. The uncertainty principle isn't just about physics, it's about epistemology, about what it means to know anything. Every time you measure something, every time you observe anything, you're interacting with it, changing it, participating in it. There's no view from nowhere. There's no objective observation from outside the system. You're always inside, always participating, always limited by the uncertainty principle. This applies to everything, not just quantum particles. When you observe a social system, you change it by observing. When you measure economic indicators, the measurement affects the economy. When you study consciousness, your consciousness is part of what you're studying. The observer and the observed are never truly separate. And Heisenberg's uncertainty principle, derived for quantum particles, points to something much more general about the limits of knowledge itself. You cannot know everything about anything. Not because you're not smart enough, not because your tools aren't good enough, but because knowledge itself has structure, has limits, has trade-offs. To know something precisely in one respect means giving up precision in complementary respects. This is built into the fabric of reality. It's fundamental. It's unavoidable. And once you really understand this, it changes how you think about everything. You stop seeking impossible certainty. You accept that reality is probabilistic, that knowledge is contextual, that observation participates in creating what's observed. You become more humble, more open, more comfortable with uncertainty. Because uncertainty isn't the opposite of knowledge. Uncertainty is part of what knowledge is. Knowing something means understanding its uncertainties, its limitations, its contextual dependencies. This is what Heisenberg gave us. Not just a mathematical inequality, not just a principle of quantum mechanics, but a profound insight into the nature of reality and knowledge itself. Certainty is a lie. The universe refuses to be completely known. And that's not a limitation to overcome. That's the way reality fundamentally is. Beautiful, uncertain, probabilistic, participatory, open. So, the next time you hold an object and feel certain about its properties, remember what Heisenberg proved. That certainty is an illusion created by scale, by averaging, by ignoring the quantum uncertainty underlying everything. Zoom in to the atomic level, and the certainty dissolves. The definiteness evaporates. What remains is probability, possibility, uncertainty. And that uncertainty, that fundamental unknowability, is not a bug. It's the most important feature of reality. The universe is uncertain because, if it weren't, if everything were completely determined, completely knowable, completely certain, there would be no room for creativity, no room for novelty, no room for anything genuinely new to emerge. The uncertainty is what makes the universe alive, dynamic, open. It's what makes the future genuinely open, rather than mechanically determined. It's what makes measurement an act of creation, rather than just revelation. Werner Heisenberg discovered this at 26 years old. He spent the rest of his life exploring its implications, defending it against critics, trying to understand what it really means for the nature of reality. He won the Nobel Prize in 1932 at 31 years old, one of the youngest recipients ever. But the prize wasn't really for the uncertainty principle specifically. It was for his creation of quantum mechanics, for matrix mechanics, for developing the mathematical framework that describes atomic behavior. The uncertainty principle fell out of that framework. It was a consequence, not the goal. But it turned out to be the most profound consequence. It's the piece of quantum mechanics that most clearly shows how radically different the quantum world is from the classical world we evolved to navigate. It's the principle that most directly challenges our intuitions, our assumptions, our deeply ingrained belief that reality is definite and knowable. And Heisenberg himself never fully reconciled with all the implications. He spent years debating with Bohr about interpretation, about what quantum mechanics really means. He struggled with the philosophical questions. He wanted to maintain scientific rigor while acknowledging the strangeness of what his equations implied. He never fully resolved these tensions. Nobody has. These questions remain open. But what's absolutely certain, ironically, is that certainty is impossible. The uncertainty principle is one of the most precisely tested, most thoroughly verified principles in all of physics. It's not speculation, it's not philosophy, it's experimental fact, confirmed thousands of times with extraordinary precision. The universe really does forbid complete knowledge. Reality really is fundamentally uncertain. This is how things are, and now you know. Now you understand that the certainty you feel in daily life is an approximation, a useful fiction that works at macroscopic scales but breaks down at the quantum level. Now you understand that the solid, definite world you perceive is built on a foundation of uncertainty, of probability, of indefiniteness. Now you understand that reality is far stranger, far more subtle, far more mysterious than it appears. This is Heisenberg's legacy. Not just an equation, not just a principle of physics, but a fundamental insight into the nature of existence itself. Certainty is a lie. The universe refuses to be completely known. And that refusal, that fundamental uncertainty, is what makes reality real, what makes the future open, what makes existence creative rather than mechanical. The uncertainty is not a flaw. The uncertainty is the point. So when you hold that object again, when you think you know exactly where it is and how fast it's moving, remember Werner Heisenberg. Remember that your certainty is built on a foundation of uncertainty, that the definiteness you perceive emerges from indefiniteness, that reality is probabilistic all the way down. And maybe, just maybe, you'll start to appreciate the profound strangeness, the irreducible mystery, the beautiful uncertainty that underlies everything. The universe doesn't want to be completely known. It resists, it refuses, it forbids certainty. And Heisenberg proved it mathematically, experimentally, definitively. Certainty is a lie, and that's the truth. The uncertain, probabilistic, indefinite truth. The only truth that matters. The truth that Heisenberg discovered, and that we can never unknow. Reality is uncertain, and now you know why. Because Werner Heisenberg proved it forever.